Hi, so my name is Kristen Gardner. I want to mentor for Alex's CHEM 251 class. My fun fact is that I actually recently just had surgery, and so I'm writing with my non-dominant hand, and so I apologize in advance for my handwriting. Oh, and the reason I want to mentor is because I really love helping people. I've mentored a lot in the past, and just with helping kids in CSS with the course material, it's just a lot of fun to teach other people chemistry, and I think that's the best way to learn. So I'm going to be talking about this unit cell question. And so I just want to note beforehand that the black spheres are the cations, and that they're located either on a corner or a face, and that the light spheres are anions, and they're all located within inside. So the first question is how many cations are present in the unit cell? And so if it's on a corner, that means that 1/8 of it is inside the cell, and that's just something that you know. And you can kind of see it, that it's like cut up in 1/8, and if you had put multiple cells together, you would be able to see that. And so the corners, you want to multiply however many corners there are by 1/8, and so you can count them. There's 1, 2, 3, 4, 5, 6, 7, 8. So you multiply that 8, and you're actually going to get 1, and then you're going to add the face ones. So the face is actually equal to 1/2, and you know that because you can see that it's kind of cut almost exactly down the middle. And so that's going to be 1/2, and multiply the number, and so there's 6 faces, and so there's going to be 1, 2, 3, 4, 5, 6. And so you're going to get 1 plus 3, which equals 4. And then for the anions present, I told you, and what it says is that they're all located inside, so you count them, 1, 2, 3, 4, so there's 4 anions. And then coordination number. So coordination number is for is anions connect to cations. So I'm just going to pick a cation. I'm going to pick this cation right here. And so as you can see that there's 2 anions bound. And so you might think that there's 2, but what you have to remember is that the unit cell is only looking at half of that cation. Only the front half of that cation is inside, and you also have to think about the back side. So if there's 2 on the front, you would think that there's 2 on the back. And another way to know that is if you look at the face cation that's on the other side, so where basically, think about it, this front half is on the inside on the other one, there's 2 cations bound. So this one shows the back side having 2 cations bound, and that one shows the front side having anions bound. Say anions bound to cations. And so that gives you 4 anions bound to each cation, which is a coordination number of 4. And so like I said, you can just do that by imagining that there was a second unit cell, and how there would be 2 anions coming off the back, and that's illustrated by looking at the cation on the far face. The next question is which unit cell is drawn. And so the first thing I like to do is look at the ratio. So there's 4 cations and 4 anions in each cell, so it's a 1-to-1 ratio. And so you can immediately block out anything that's not a 1-to-1 ratio. And then when it comes between zinc and calcium, you can look at that radius, because if you look at the radius ratio, so which is cation divided by anion, you're going to get a number. So basically you just divide this lithium and sodium by, is that what it is? Or it's zinc and calcium, zinc and calcium by sulfur. So you just do 88 divided by 170 and 114 divided by 170. And I'm not going to do the ratio, but basically you were taught in class and memorized a list of numbers for the ratios. And so the smallest group of numbers, when you divide 88 divided by 170, that's what that one's going to fall into, associated with coordination of 4 or a tetrahedral molecule. And so that's how you know that this is zinc sulfide. Like I said, you can do all of the math. And then finally, the last thing you're going to do is look at which one you expect to have a lower melting point. So you might think you'd be able to use Paget's rules, but Paget's rules requires you to have the same sized cation. Calcium is +2 and lithium is +1. So you can't do that. But what you can do is use charge density. Charge density is equal to the number of the charge times 1.6 times 10 to the negative 19 divided by 4/3 pi r cubed. I'm not going to plug in all the numbers because it's going to be ugly, but n is just equal to this charge. So for calcium, you'd plug in 2 for n, and for lithium, you'd plug in 1. And then for the radius, you can plug in these numbers. So 90 for lithium and 114 for calcium, and you can literally just directly plug them in. There's no changing of units or anything. And so you'll get lithium's number to be 5.29 times 10 to the negative 26. And you'll get calcium's to be 5.16 times 10 to the negative 26. And so lithium's is higher, and so increased charge density is more covalent, and so if it's more covalent, it's going to have a lower melting point.